Good afternoon, ma'am.
Good afternoon, sir. Very warm welcome, sir, in this FDP, in this 6-day induction and reflection program on cybersecurity and autonomy. So, a very warm welcome to you, sir, in this session. I just give a brief introduction about the Pilli, sir. He is associate professor in the Department of Computer Science of Engineering in Malviya National Institute of Technology, Jaipur. M.Tech from Birla Institute of Technology, Ranchi in 2001. PhD from the Indian Institute of Technology, Roorkee for his thesis on a framework for network forensic analysis in 2012. Awarded the ISEA Fellowship by the Department of Information Technology, Government of India for his research in information security. He is having 24 plus years of teaching experience, research and administrative experiences. Officiated as head department of CSE in MNIT from June 2019 to June 2021. Dean Rajasthan ILD Skill University, Jaipur since June 2019. Co-coordinator for the Electronic and ICT Academy, sponsored by Ministry of Electronics and IT, Government of India since December 2015. Regional Coordinator, Regional Academic Center for Space by ISRO at MNIT. Supervised 7 PhD degrees, 38 MTech degree, MTech theses or dissertations, and around 35 BTech projects. Currently guiding 7 PhD and 2 MTech students in the area of interest, that is the security forensic, cloud computing, big data, IoT, blockchain, and quantum computing. He has presented 90 plus papers in international journals and conferences. All are the reputed journals, that is Scopus or SCI Index journals. He is the member of editorial board of Forensic Science International, Digital Investigation of Elsevier Journal, and he has published there are several publications in IEEE transactions on cloud computing and IEEE communication services and tutorials having IF factor, that is 25.25, and co-authored 2 research reference books. Senior member of IEEE, ACM, and life membership of CSI, and member of Quantum Ecosystem Technology Council of India, that is QETCI. So I would like to again welcome you, sir, in this FDP. And today, sir will take this session on blockchain management system and survey. So welcome you, sir.
Thank you, Professor Dolly Shukla, for inviting me for this important talk. And I'm happy that many of you have assembled here. And in this afternoon time, I don't know how much you'll be able to follow, but then I would want to keep your attention, right? Because this is a very important topic, and for India also it is very important. So if you feel you want to do something for our country, that is something that which is important for us. So please. Try to pay attention and then look at what you can do, because many times we hear these terms, we are aware of what is a blockchain, what is a cloud, what is IoT, and a lot of these things, we are quantum. But then how it is going to help our country is something that we need to really look at. And we are a little bit lagging behind. If you ask me in the curriculum of cloud computing, if you look at it, it is a little behind schedule. So that is something that you can try to look at. So let's take it forward, and I'll just share my slides. At the end of the talk, I will share the slides with Dr. Dolly, and she will share them with the participants, right? So you don't worry, but then you can make notes along while the lecture is going on, right? So, and then we will also do a small demo of blockchain in between, so that you can understand what is the actual working. Because security issues I'm directly dealing, but before that I will just briefly introduce some concepts to you as well. So are my slides visible?
Yes, sir, it is visible.
Yeah, you are able to see that, right? Right. So we'll start. Let's take this now. Right. So if you look at a blockchain, if you look at the words, these are the words that come to our notice: cryptocurrency, blockchain, uh, Bitcoin, public ledger, right, and internet, exchange of money, payments, network protocols. These are the words that are there. There are various names which are there, like Litecoin, Bitcoin, Ethereum, and some of these words which are quite popular, right? So maybe if you look at it, Bitcoin basically started with you know. Given by a person called Satoshi Nakamoto. He wrote a paper and he blogged about, right. So he wrote about what do you call the Bitcoin concept, cryptocurrency. So the basic idea of Bitcoin was that a lot of banks, when you see bank transactions, when you want to transfer money from one bank to the other bank, or earlier days you had something called demand draft, right. So most of the time when you are paying the applications, you are sending out applications or applying for some job or something, then you had to send a demand draft along with the application, right. Now, of course, you can make a NEFT transaction or a RTGS, or you don't do RTGS anyway, but IMPS or NEFT transactions you do, or now you can very easily pay using Paytm or Google Pay. You know, they are some of them are also accepting that kind of thing. But then all of them come with a transaction fee. So whenever you are making any transactions, presently these online wallets are not taking any transaction fee, but over a period of time, slowly that will also come. As of now, they are very happy with the amounts being transferred through their hands, and the kind of resource that they are able to generate, and the number of transactions that they are able to get. So in a similar sense, blockchain initially was introduced to reduce the transaction fee. They did not want to have any transaction. They wanted to make all transactions, but they don't want to have any transaction fee. So that was the basic this thing. As Times of India, Times of London talks about Bitcoin's libertarian roots, where there are so many transactions are handled, but there is no transaction fee that is charged, right? So basically, if you look at what is blockchain or what is Bitcoin, where basically you have to solve an encryption formula, right? And that requires extreme amounts of computing power. And what is the motivation to solve this encryption formula or create a list of blocks or a linked list of blocks or a blockchain? So you have to solve the formula. You can earn some Bitcoins, right? So the motivation is you will get some Bitcoins free of cost, right? And about 21 million Bitcoins will ever exist is what is the calculation, and about 80% have been mined and some more are remaining, right? So if you look at Bitcoin denominations also, you have, milli Bitcoins, micro Bitcoins, and then you also have Satoshis. Satoshi is the person who, he's not a real individual. It is what you call a pen name or a pseudonym name that is there. It's not his real name, right? So that's what you can try to look at, right? So if you want to buy Bitcoins, now how do I get hold of Bitcoins is what you can think. You can buy it from a Bitcoin exchange. Like you have stock exchanges where you can go and buy different stocks. You can buy them online also. We call them DMAT trading, right? So similarly, you can go to a Bitcoin exchange. You don't have to physically go there. You can just log in, create an account on a Bitcoin exchange. Some of the examples are Binance, and a lot of so many Bitcoin exchanges are there. So you can then you can pay in Indian rupees and procure Bitcoins, and then you can keep them in your wallet, like just like your Google Pay wallet or Paytm wallet or Phone Pay wallet, right? So the second way is you can have a friend transfer to your Bitcoin address. So whenever you create a Bitcoin exchange, you create a wallet, you get what is called a Bitcoin address, and then this address you can share with your friends, and your friend can transfer it to your Bitcoin address. Usually, it is a 35-bit hexadecimal number, 35-bit digits. So 35 digits you can store and remember, and then you can copy paste it. You can create a QR code for that and send it across, right? The last option is to mine a Bitcoin. We will look at this also, what is mining of a Bitcoin. You can do that. And currently, if you want to create one block, you need you have to have a power which calculates 114 million terahashes. 114 million terahashes per second. Of course, now it's about 150 million, I think. So what is a hash rate? It is a measure of how many times the Bitcoin network can attempt to solve the proof of work puzzle. So So that is something that you can look at. How many times the Bitcoin network can attempt to solve the proof of work puzzle per second. The more hashing power in the network, the greater its security and overall resistance to 51% attack. So that is something that you can look at. And then the Bitcoin current hash rate is coming down. Earlier it was 180. Now I think it is 150 around like that. In May 2021, because China had put up a mining ban. Right? So usually this is going down. Bitcoin rewards were given earlier. 50 Bitcoins were given when Satoshi created the first block. He got 50 Bitcoins. 4 years later, sometime in November 2012, the reward came down to 25 Bitcoins. Slowly it came down to 12.5 Bitcoins. Because the popularity of Bitcoin cost is increasing, this is coming down. I'm trying to introduce this because if you try to understand what is a blockchain is a public ledger. Now, you would have heard the word ledger. Any accounts people will know what is a ledger, right? If you have been associated with accounts people at any point of time, you will see that they write ledgers. They write the account ledgers, right? Or you go to a bank official maintains ledgers. Maybe, I don't know, maybe 20 years ago, if you had a bank account, you had to go and have a passbook and you would get the printout of your statement, right? And now you don't actually go to a bank now to get a statement printout because you do the online banking and you go and open a bank account and see the banking transactions and then you make the transactions, right? So all the transactions list is said to be a ledger. Now, when you talk about a blockchain is said to be a public ledger. Okay, the technology that blockchain is based on is called distributed ledger technology. It's called DLT, distributed ledger technology. And on this distributed ledger technology, you have what is called this. The account is open, but it's public ledger. So when you say public ledger, does it mean all my accounts are public? Anybody can see? Yes, all your accounts are public, and anybody can see all the transactions that you are making. Right? So that is something which is surprising. So many of you may say, oh, my bank account, if it is public, I won't like it, right? But then see, just another issue that you can link up with that is the account details are public, but who holds the account, that information is not there. So that is where there is no problem. If nobody knows your name, nobody knows your bank account, nobody knows whose bank account it is, what happens even if your details are on the internet, but nobody knows that it belongs to you, so there's no issue, right? So that is what is a public ledger. So as you see, you can now if you want to look at the blockchain, which is basically Bitcoin related, because after Bitcoin there are so many other coins which have come in, right? Popular ones are Ethereum and Monero and other things like that. So you have, and then if you want to look at blockchains, the ledger that you want, you can go to these websites called blockchain.info and blockexplorer.com. Straight away, you can see the status as on date, right? So this is how a diagram, a snapshot will look like. So the number of blocks, the latest block is shown on the top, and who created that block is written. We will talk about mining. We talked about miners, right? You can mine a block and you will get some reward. Now, presently, you get about 6.5, 6/1/4 of the 6.5, I think, right? 6/1/4 of the block that you get, right? So when you mine it, so now miners, it's very difficult to do it alone. So they are forming pools of miners, right? Few miners are coming together, putting all their resources together and doing it. So that is what we do. And then it holds, every block holds some transactions. All these transactions are listed. And then the size of all these transactions is around 1 MB, right? And then the weight of this is calculated. Then average transactions, now earlier there was no transaction fee, but slowly they introduced this transaction fee because slowly after this 6/1/4 Bitcoins is not much money. So it is coming down. So people started attracting this thing using the transaction fee. And then this is the reward as we see, and the transaction fee is added here. And then the timestamp at which the block is created. This is fixed. Now nobody can change these after certain time is done. Then these blocks are final. So this was a couple of things. Yesterday night I took a snapshot of this. So if you go and see it, you'll have about 717 and something more like that, right? Maybe 3-4 days ago I took this snapshot, right? I'll show you on any website. You can go and just take this, and you'll be able to see these things. And then this is the hash We'll discuss what this hash stands for. It was created 7 minutes ago, and then it was created by this miner, and then the size was something like this. So different sizes are there, 1.5 MB to 1 to 1.5 MB roughly, and then these are the numbers that till now these many blocks have been created in a blockchain, right? So if you look at a single transaction, how does it look like? So this is a block. How does it look like? So these are the things that are there. A block will have a hash. Every block will have a hash, and the hash is built using the previous block hash, right? The previous block hash, and the next block, of course, is not have any value. This is the block hash, is same as this block hash, as you see, 7053 here. So you have 7053 here. So this block hash and this block hash, this is calculated based on the previous block hash. Next block hash is anyway not going to do, but the next block hash will refer the previous block hash. The Merkle root is based on all the transactions. So here you have transaction count 600 and 604 transactions are there. The 604 transactions you create into a Merkle tree. You create a Merkle tree, a data structure of a Merkle tree. Of course, Merkle tree you can read from data structures. It is beyond the scope of the lecture today. And this value is called the Merkle root, which is the hash of its root. You create a tree. The tree will have a root which will be on the top. And on the top, you take the hash of that value, you will get a Merkle root value. So how do you calculate this, what do you call the block hash? The block hash will be dependent on the previous block, the Merkle root, and a value called the nonce value, right? You combine this and give it to an algorithm called mining algorithm. And the mining algorithm will read the previous block hash, the Merkle root, and it supplies different nonce values, and the algorithm will result in a value like this. So what should happen is you should get a hash value with preceding 19 preceding zeros. So there must be some preceding zeros which must be there, right? It depends upon the difficulty of block mining. So the 19 preceding zeros are shown, and then this is what is you should get a value which is less than a certain value, which is called the target value. So the till you get the target value, you keep on changing the nonce values, so that you will get a hash value which is having usually 19 zeros or 18, 19, 20 zeros at the beginning, and then some value. So this is what has to be created, right? So as you look at it, these are the transactions. You can have this is the transaction hash. These are the addresses. These are the values of the transaction. This is the and then you have the output transactions, and this is the amount that is received. So you can look at how many bytes are there, how much is the transaction fee, and the timestamp is all mentioned here. So initially Bitcoin is gaining value. Satoshi transferred money to his friend Hal Finney, and later somebody was allowed to buy a pizza which was $25 for worth 10,000 Bitcoins, right? So now if you have 10,000 Bitcoins, maybe if you have 25 Bitcoins, you will get 10,000 pizza, more than that in fact, right? So that's the kind of thing. But then of course, Mt. Gox was created as a Bitcoin exchange, but then they lost Bitcoins and they declared bankruptcy. So these things can happen. So this is the thing. And then by and large, if you look at it, who will use Bitcoins? And in fact, where did Bitcoin become popular? Bitcoin became popular when we used what is called this the WannaCry virus had infected and encrypted the systems. So if you want to decrypt the systems, people could identify whose system they encrypted, and if they wanted the system should be decrypted, so they realized that they have to get this thing done, and then they wanted to do it, right? So they had this option of trying to send that code, and you had to pay money in Bitcoins. That's how Bitcoin became very famous, right? So and one of the things that happened was they created something called a Silk Route, where they were selling brown sugar and some of these drugs, like cannabis and other things, and they were also maybe sending pornographic items and fireworks, guns, ammunition, and all that were sold using Silk Road, and that was on the Tor networks, right? So Tor and blockchain will be a very powerful network. So you can try to understand how it goes, right? So the Bitcoin boom, as you look at it, it's about 13 lakhs in December 2017, and it moved on. I will show you some latest statistics. This I took 2-3 days ago. So the Bitcoin value on December 17th was 19.363. This was 2017, right? 2017 December, just before this thing. So December 17, 2017, it was 19 lakhs. So that was what early morning. So that was a peak that you got here. So that was December this thing. Later, as you see, the next peak came somewhere in 14th April. It was 63 lakhs. Right, so 14th April it became 63 lakhs, and maybe currently if you look at it, it is 43 lakhs. But of course, again, sometime later, 10th November, as you look at it, in 10th November, this was 10th of November, you see another peak, right? In 10th of November, as you see that peak, it was something like 67 lakhs. So just understand the rate at which things are increasing. Of course, it has now come down to 43, 67. It has come down to 43 lakhs. So that's the kind of money that is involved. And then a lot of people are accepting, like MicroStrategy, Square, and all. So a lot of people are investing in Bitcoins. JP Morgan, Tesla, BlackRock, and then PayPal says you can buy and use using Bitcoins. And Bitcoin halving was done in May 2020. MasterCard will allow some cryptocurrencies as payment methods. So these are things which are coming up, right? Then there are so many altcoins which are called alternate coins. Ethereum is one of the famous one. Ripple is another famous one. You have Litecoin, Zcash, Dash, and our Deshi Lakshmi coin is also there. And you have also a coin called Monero. Like that, there are so many coins which are there. Some of them are listed here: Bitcoin, Binance Coin, Cardano, Tether is there. Dogecoin is one thing which is very useful, which is used, right? Polkadot, and so there are so many coins that you can look at. So why does Bitcoin matter? Because it's a cryptocurrency. It is purely digital. It is not controlled by a central entity. If you look at Indian rupees, a 500 rupee note or a 2000 rupee note is controlled by the Reserve Bank of India, right? There's a central agency. In government, in US, you have the FBI and Federal Bank and other things which are behind that, right? So it takes care of double spending issue. We'll discuss double spending issue in some time. So basically, there is no centralized control. Now, if you have a 1,000 rupee note today, people will arrest you because 1,000 rupees is an illegal tender now, right? You should not have a 1,000 rupee note, right? Indian rupees 1,000 should not be there with you because it is an illegal tender. But you can have 500 and 2,000 rupee note, which are legal tenders. So Bitcoin per se is not a legal tender in India, but at the same time, it is not illegal. You can buy and sell Bitcoins. There is absolutely no problem. But then someday later, government will ask, where did you buy these Bitcoins from, and can you show the accounts? So if you directly buy or if you directly trade on the blockchain, there is no problem. But if you trade on the exchanges will ask you to do what is called KYC. Most of the banks also do what is called KYC, that is know your customer. So this KYC is done. So once the KYC is done by the exchanges, the KYCs will give to government all the Bitcoins that you buy or any crypto coin that you buy, any cryptocurrency that you buy. So you will have to give account to that. It is like your income tax statement. At the end of the income tax statement, you write that statement and you mention, right? So that's how it is. So the peer-to-peer network in which transactions directly between users, there is no intermediary. So that is what we can look at. And transactions are verified by network users. These are miners who verify the transactions, right? So that's what you can try to look at. And transactions are recorded as block in public ledger. That is what is called blockchain. How does a blockchain look like? A blockchain looks like this. It's like a linked list. So it's a method of storing data among multiple parties that ensures data integrity. The distributed ledger or shared database is there. So everyone holds a copy of the entire log history of transactions. A distributed ledger is immutable, and the distributed ledger is timestamped, right? So that's what it looks like. So everyone holds a copy of the entire log history of transactions. So that's something that is there, and then it's immutable and it is timestamped. So that's something that you can try to look at. So that's what is a distributed ledger. So let me take you through this. The slides are there. The website is mentioned here, but let me take you through that web link so that you can easily understand. Or the next few slides, instead of discussing on the slides, I will show it on the demo of a blockchain, right? So let me take you there. can share that part. So are you able to see my screen? Yes?
Yes, sir.
Yeah. So this is andersbrownworth.com. It is a blockchain demo. So you can look at the SHA-256 is simple hash, secure hash algorithm. 256 is presently used for hashing in blockchain also. So if you just imagine, you see these values here, and if I type any value, let us say my name here. So each character that I type, the hash value is changing, right? Are you able to see that? So that is what is hash. So hash is basically you give some input. So these are kind of transactions that are copied here in this data field, and a hash of that is calculated. So that is what is the meaning of a hash. Now let us look at the next step. If it's a block, so there is a block. Block has a number, right? We saw that numbers, 7 lakh something. Then we talked about a nonce. So data will be transactions, and a hash value is generated, right? So if you look at these hash values, so you will have, see, here we have put 4 zeros, right? Of course, not 4 zeros. Usually on the actual blockchain, it will be 19 zeros or 20 zeros. Preceding should be 19 zeros starting. But here for a demo purpose, we are using 4 zeros to show a sample, right? So what happens now? This is looking green. That means this block is correct value. So let us say I make a transaction Pilli. I will give let us say some 100 rupees, right? Let us say 100 rupees, right? So this transaction has been done, right? So maybe this is how a transaction looks like, right? So what happens is now this hash value has changed, right? So what I have to do is I have to mine this so that this nonce value changes. Block number is anyway fixed. This nonce value has to change so that I will get a target value. Target value means first 4 must be 0. So I am just asking this mining algorithm to include this data and get me a value which will have first 4 zeros. Of course, sometimes you may have 5 zeros also, because the next string may start with a 0, so it looks like 5 zeros, right? So the nonce value has changed. Earlier the nonce value was something else. Now the nonce value is something else. Let us say I add one more transaction. Let us say something like that, right? So some transaction like that. Now again this has changed. So just remember this 46737. Now if I ask the mining algorithm, it calculates a new hash value. Here it is 4 zeros, and the hash value as nonce has changed, right? So that is how it looks like. Now if you look at what is a blockchain, now blockchain will be something like this. So you can see the diagram. Blockchain will have something like this, where the first block, second block, third block, these are multiple blocks, and then different nonce values. The first block will not have any previous block anyway, because there is a first block. The first block's hash value is copied in the previous hash, and this hash value is copied in the previous hash here. This will be the next hash value, which is going to be after that, right? So you have these 4 blocks, and then you have the nonce values here, right? So if you make any change in one transaction, let us say these transactions are now fixed, all these blocks are generated. But let us say if I make a change in one transaction somewhere in between, let us say I make a change of transaction here. Let us say I say Pilli, okay, some 100, right? Some transaction is made. So what has happened? This block is anyway there. This also will get changed, and all the subsequent blocks, they all will get changed. So let me try to solve this problem. How do I do it? I have to mine this algorithm. So I get 4 zeros here, and this hash value is moved here, right? Automatically. Now again, I'll have to mine this also. So if I have to make one change, I have to change all the blocks that are coming after this. So this is one property which gives us a lot of strength. Now what can happen? If you want to make one transaction change somewhere, there is it is called an avalanche effect. You have to make so many changes in transaction. Okay, if you have a blockchain with you and you can make those transaction changes, but let us say now when we go for a distributed blockchain. So in the distributed blockchain, what happens is you can't make these changes, right? So why? Because you will have one block like this, peer A, then peer B will have another blockchain, same copy. If you see the previous hash values, the previous hash value will be same. If you see this is 12FA, here also you see 12FA, and here also you see it is 12FA, right? So this is also 12FA. So like that, there are every peer will have one copy of the blockchain, and then it is very difficult to look at that. So now we will look at how transactions are. This is how transactions will look like, right? So there will be some transactions. You are sending so many, here it is mentioned as dollars, but in case of this thing, it will be like bitcoins. So many bitcoins are sent from so and so person to so and so person. These names are mentioned here, but actually in the case of blockchain, the public addresses are mentioned, right? The public address of an individual. It will be like your email address, which is public. Anybody can see the email. Till he doesn't know what is the password, there is no harm, right? Many of your friends, in the end, in fact, my email is known to everybody. If somebody goes and searches on our website, they will be able to get my email. Everybody knows my email. But if somebody knows my password, then I'll have to worry. So that is what is exactly like a blockchain. So it's a public ledger, and there are so many web addresses that are mentioned. Public addresses, no problem. If a private key is known, then it will be a problem. They can make transactions on your. It is like somebody knows your internet banking ID, no problem. If somebody knows your internet banking password, then it's an issue. So these are transactions which are shown like this. So here they have put names, but there it's actually numbers, and then you can make those transactions. So that is how it looks like, right? So the tokens, the same thing is maintained in all the blockchains, right? Then this Coinbase means the initial when the block is created, you get some coins. Like now 6/1/4 of a bit, so many bitcoins are given. When the earlier it was 12.5 bitcoins, earlier before that it was 25 bitcoins were given as an initial thing. So that was called the Coinbase. And you can go through this. There is a good video tutorial also on YouTube by andersbrownworth.com. So very easy to understand. And also see it in a simulated fashion, right? So that is something that you can try to look at. So hopefully you understand it. Maybe it's very difficult to understand in very less time. So what you can try to do is you can try to go through that website and check it out, and then understand how you are able to look at it, and then pick up, practice, and then you can get more clarity, right? You can watch the video. It's called, I think, Blockchain 101 on YouTube, and then followed by this web link you can follow, and then you can get that address. Maybe towards the end of the lecture I will copy that. It's there on the slides anyway, so you can try to look at that, right? Let's go back to the thing that I was presenting. Okay, so let's go back to the slides. So here, you have seen this part, hashing we have seen on this address. So you can go and search here. And transactions are messages that let users spend their bitcoins. So this is the hash of the transaction. And then this is the address, public address. These are the number of bitcoins which have to be sent to these addresses. And they have to be given to them. And then some transaction fee is charged. And the timestamp is mentioned. This is the transaction fee and the amount of Bitcoin that is transferred. So this is how transactions look like, right? In Bitcoin transaction, each input spends the Bitcoins paid to a previous output. It is called unspent transaction output, right? It is called UTXO, unspent transaction output. This is the main parts of the transaction 0 and the main part of the transaction 1, as you see. So the outputs of this thing, the previous output is spent in the present input, right? So that is something that you can try to look at it. So that is very important, right? So that is each output waits as an unspent transaction output until a later input spends it. So there is one set of transactions which are available, so they have to be spent. So that is what is called a UTXO. So you have a UTXO data set. So whenever a user wants to spend Bitcoins, a transaction is created, then you can send to all your intermediate peers, immediate peers. Transactions are verified, and if it is validated, it is sent to their neighboring peers. The transaction is broadcasted in the entire P2P network, right? So there are, there are two databases that is called a UTXO set. UTXO set is a file that contains all the spendable outputs that are available to be spent in a transaction. So this is what is UTXO set. We just discussed what is UTXO. So UTXO set is a database which contains all the spendable outputs that are available to be spent in a transaction. Then there's another database called mempool. Mempool is a file that contains transactions which are received by peer nodes but are yet to be included in any block. They are called unconfirmed transactions. A file that contains transactions which are received by peer nodes but are yet to be included in any block. So their unconfirmed transactions are said to be mempool. The confirmed transactions are said to be UTXO set, right? So block is basically linked to the previous block by making it a chain of blocks. And each block contains, as I mentioned, the previous block hash, the nonce value, and the Merkle root. So based on these three values, you calculate what is called a block header. So it is said to be block ID is equal to hash of the block header, which is hash of the previous block hash, followed by Merkle root and nonce. You take these three values and you calculate the block header, right? So blocks are chained together using the previous block as you look at it. So that's why blockchain is immutable, because if you want to make any change, it causes changes in the subsequent blocks, which is very difficult to change. So it prevents double spending of the blocks. Now you may have the question, what is Merkle root? So Merkle root combines the hash values of transactions together until there is a singular value. So there are multiple data points, all those data points. So there may be so many transactions. Each transaction, you create a hash value. So you combine two transactions and create a next hash value, and subsequently you move it upwards. So that's how it you have. So an effective mechanism is to summarize transactions in a block, verify the presence of a transaction in a block, provide immutability of transactions since the Merkle root hash will not match if change is made to any transaction. So this is how it looks like, right? So all the transactions are put together. So you summarize them, then you verify the presence of a transaction in a block, and you provide immutability of transactions because the Merkle root hash will not match if one change is made to any transaction. So this is how it looks like. So you have transaction 1, transaction 0, transaction 1, transaction 2, and so on. So for each of them, you get the hash values. Then you combine these two hash values and get a new hash. Then this tree grows up, and each of these transactions will get clubbed together, and finally you get one transaction value, which you will call it the root. The hash of these two roots is said to be a Merkle root, right? So this whole tree is said to be Merkle tree. The root is said to be Merkle root, right? So we discussed this also as we saw this block, and as we saw in this thing. So we saw that we are having a block here. We saw this diagram. So you may have this the understanding already as I shown. So now the important process, as I told you, what is mining. So why I'm giving you this basic idea is, if you understand what is this concept, because most of the security attacks that happen on these concepts only. So there is usually, as we look at in cyber security or network security, anytime you look at the attacks will happen on the security aspects only, right? There's a protocol, there is a set of rules to be followed, and those protocols are compromised, right? Those rules are compromised, by which you can actually an attack or a vulnerability is successful. In this case also, in a similar sense, as we look at it, we look at this blockchain concepts as we look at it. So when these algorithms are attacked, so you can have a change. So that's what you can look at, right? So here, mining is the process of finding the new block. So when you add a new block, miners need to verify it by solving a computationally difficult proof of work puzzle. I briefly explained what the proof of work puzzle is, right? You will have 3 inputs to the proof of work puzzle, and you'll have 1 output. What are the 3 inputs? The 3 inputs are previous hash value, a Merkle root value, and you'll have to guess a nonce value. Based on these 3 values, once you give it as input to the proof of work puzzle, the proof of work puzzle will give you 1 output, and that output is a target value, or it will give you 1 value which is having some 19 preceding zeros. It should be less than the target value. If it is yes, no problem. If it is not, then change the nonce and recalculate the result, and then you must check whether it is less than the target value. Once it is less than the target value, the block can be added to the network. So this goes on, and lot of these the proof of work algorithm involves scanning for a value called the nonce. So when it is hashed, results in a hash beginning with a number of zeros. So that is what is a target value. So you need to get that target value. So this here in this case it was 4 zeros. So if you make any change in one transaction, so now slowly we are entering the concept of security. If you want to make changes in the transactions, then it will result in an avalanche effect. There is a slight change in input can cause significant and unpredicted change in output. So that's an avalanche effect that you can try to look at. So change in data in a transaction is change in the hash of a transaction, change in the hash of the block, and change in the hash of the next block. So this is how the change is moving on. So change in data in a transaction, change in the hash of a transaction, change in the hash of the block, change in the hash of the next block. So if you make one change in a transaction, it will change in the hash of the transaction. That is a Merkle root. So it will change in the hash of the block, because Merkle root is changed means hash of the block is changed. If the hash of this block is changed, the hash of the next block is changed, because the hash of the next block is depending on the previous block. So this is something that we can try to look at it. So the difficult to change data in a block without mining successive blocks. So that's what you can try to look at. A Bitcoin miner must download the entire Bitcoin blockchain. It must verify incoming transactions. You must create a block, find a valid nonce, broadcast your block, and you'll get your profit, right? So if you now, as a researcher, what you should do if you want to work with blockchains, you should download the entire blockchain, right? And you should identify how do I connect to these two databases, right? UTXO set and mempool. And then you should look at how can I get all the incoming transactions. And then, of course, creating a block will require huge resources, and then it's difficult. But then you can try to understand the whole process of how it happens, and then you can find a valid nonce. Once you find the valid nonce, you broadcast your block, and then you get the profit. That is, a blockchain will give you 6.25 bitcoins, and that 6.25 bitcoins you can go to an exchange and get your cash. So this is something, the whole mining process is like this. So you get all the transactions, check whether all the transactions are valid, bundle the transactions into a block, create a hash, create a Merkle tree, create the hash, and find the nonce value by solving the proof of work problem, get the nonce value and find out whether that value is less than the target value. When the solution is found, the new block is added and propagated into the network, right? So how does the proof of mining algorithm look like? So you propose a block. So header of the most recent blocks is obtained. When you propose a new block, you take a list of transactions, you calculate the Merkle tree, and you get the Merkle root value. So here you will get the Merkle root value, here you get the header of the most recent block, and you have to guess some nonce value, and then you combine and hash of them, you get a hash value. Is it less than the target value? If it is yes, then proof of work is solved. If it is no, you go back and increment and try again, and then get a new nonce value, again combine it, get a hash value, check whether it is less than the target value. If it is not less than the target value, change the value of nonce. These two will remain constant, only the nonce value will keep changing, right? So this is an algorithm which has to repeatedly be done, and so 114 million times it should be done in 1 second. Then you will have the speed to handle this thing, right? So this is a slightly bigger diagram. So what is the target value? Target value is you cannot create as many blocks as you want. So you have to create only 10 blocks in 1 hour, like 6 to 7 blocks in 1 hour. To compensate for increasing hardware speed and varying interest in running nodes over a period of time, the proof of work difficulty is determined by a moving average, targeting an average number of blocks per hour. So per hour you can have maximum of 6. So whenever there are 7, because usually block is mined once every 10 minutes on an average. So usually it should be 6 blocks in 1 hour, but then you can also exceed. So presently that is what it is. And then it adjusts every 2016 blocks. So that is every 2 weeks the timing is adjusted. So if more blocks are getting created, the difficulty level will increase. Amazing, right? So that is something which that Satoshi Nakamoto's brain just imagined, right? All these things were coded as an algorithm and given, right? So the mining algorithm, the calculation of the target value, the nonce value, and all. So these are all very good values. And then everything is automatically done by volunteers, right? Miners are volunteers. Of course, they're earning a lot of money by working on Bitcoin strategies, but then yes, they get what is called they get a lot of rewards. But then yes, at the same time these things continue. So mining algorithm is one wonderful concept. This target value is one wonderful concept, and the target value being fluctuating. The target value increases; it becomes more strict when people are creating more coins by guessing, right? So what happens? The target value becomes difficult. It is difficult to get such a difficult answer, and then immediately it changes. So that is something. So these are all nobody is again sitting and monitoring this, right? It is automatic, and that is the greatest this thing about it, right? So there is another concept here I am trying to introduce. Mining algorithms can be hardware implemented, right? So earlier people started using on CPUs. So you have one CPU, one board. So earlier people were working with blockchain, and then they were creating. If you have one CPU, you could add only one block. Over a period of time, people wanted to add more blocks because more money they want. So what they did, they started using clusters. Then they started using GPUs, graphical processing units. CPU has less cores and GPUs have more cores. More cores means more faster you can do, parallel processing you can do, right? FPGA, fully programmable gate arrays you can use, or you can use what is called ASICs. ASICs means application specific integrated circuits. So these ASICs help you in actually creating a better role. So that's what you can. So ASIC is basically the entire mining algorithm is hard coded as a chip. So the chip will do only one thing. It will run the mining algorithm. It will take these three inputs and give you one output, right? And that's what you want. It doesn't do anything else. So there is no other code that is there. Once the program starts, only does only one job, right? And then it never gets tired. So when Bitcoin was first released, it was 100 Bitcoins in a day. At CPU level also you can do it. But as slowly things became difficult, right? So people started using ASICs, and specialized computers are used. So ASIC is a microchip, as I already mentioned. So it executes the hashing algorithm as quickly as possible, but then it draws a lot of power, lot of electricity is consumed. So why China stopped mining of Bitcoins? Because a lot of electricity bills are being generated, right? So cooperating miners pool together agree to share the block rewards in proportion to the contributed mining power. So what happens is, if you get 6.25 Bitcoins, they share among themselves depending on the resource that they have put in. So that is what is called a pool. So another very interesting concept. So as the mining algorithm become easy, mining becomes easy when you're able to generate ASICs, and then you are able to get powerful control. So you are able to generate more power. You are able to do more faster generation, and you are able to get that thing. So that's one thing you can look at. So the ASIC resistant mining algorithms were developed, right? ASIC resistant mining. So if you are creating ASICs, the mining algorithm is becoming ASIC resistant. So you create an ASIC also, the mining algorithm will take the same time. So these are memory hard algorithms which are developed. So just imagine a wonderful research is going on as far as this blockchain is concerned. So you have hash cache, which has come up. Then proof of work is replaced by proof of stake algorithm. This is the Ethereum algorithm that has come up. So you can look at that. You have equihash, which is also there. You can look at the GitHub and you can do that. Ethash is the current mining algorithm also. And then RandomX is another mining algorithm which is adopted by Monero, right? So these are these ASIC resistant mining algorithms. Now, I just introduced you to proof of stake algorithm, and you'll ask me, what is proof of stake? What is proof of stake? You have shard chains. So very recently, maybe 1 year now, December 2020 is also recent if you look at the thing, but it's now 1 year old. They rolled out as a beacon chain called shard chains. So rather than just one blockchain, Ethereum has become 64 blockchains all running in parallel. So what has happened is earlier more transactions were getting delayed to be added to the blocks. Now when 64 blockchains are running in parallel, you can handle more instructions, more transactions per second. So that's how this is there. And miners are not chosen depending on the power that they have, or the speed at which they are able to find that nonce value and the target value. But miners are chosen depending on the relative value of coins held in the miner's wallet. So miner has a wallet, and that miner's wallet will have some coins, and those coins have to be thrown. So the length of the time that a miner has held coins in their wallet, how many coins you have, and how much of time the miner has held their coins in their wallet. So accordingly, you have a preference to the miners who will get selected, right? More coins you have and more time you have to keep it, more likely you will want the system to succeed. So hence you want expense to be. So that's what. So you are expecting honest behavior, and hence that will also be taken care of. Now we'll talk about some attacks. So there are double spending attack. So Gillen has 10 Bitcoins and he wants to give it to Brian, He wants to use the same bitcoins to Nadir also. So both the people. So what is happening? Gillen is doing a double spending attack. When does a double spending attack become successful? So you can have a buyer like Gillen who wants to buy from Nadir also and who wants to buy from Brian also. She promises the two gentlemen, the two sellers, that you can please sell me these items and I will pay you in this Bitcoin transaction. So this success depends when these two two transactions, if they go to the same block, the same block will not accept it, because it will check that you have so much of money and you have made this transaction. Now you have so much of money. And the next transaction says, I am in this, I have so much of money, and now I make this transaction. It says, no, this transaction is already done. So now you don't have $10, right? So, but then when you look at this, if these two blocks will go into two different blocks, two transactions are coming into the mempool, but when the transactions are picked up, they are picked up into two different blocks. At that time, if they are almost blocked at the approximate time, and then the seller gets information that yes, transaction is done. But before he waits for the confirmation, what he does, he sends the services. Earlier, after you place the order, it will take some days before the transactions are made. But here, these are made immediately. These transactions are made immediately, and hence you have later. So the seller can send. Now, maybe if the item is like, let us say, some software or some key has to be given, or some item has to be sent online, right? So what happens immediately? After I see the confirmation of the transaction, I don't wait till it becomes a block and it is added and finally the transactions are done. So before that, I make that. So what happens is, if at a later time the transactions are rejected by the network, I would have already sent that licenses or software to be downloaded or application that is to be downloaded, and that will become a problem. It is something like this. So whenever a block is added, there are other miners who will confirm the block, right? So till there are 7 confirmations, this block doesn't get added, right? So what happens? This fellow has made this transaction, same Bitcoin transaction to seller A and seller B. Fortunately, they went into 2 different blocks, and the transaction, if they were in the same block, immediately it gets verified. But here, as they have gone to 2 different blocks, this gets added and this is waiting confirmation. But before the confirmation, seller B says, okay, I received my transaction, so let me pay him, or let me clear that work. So he clears the work, but later he feels that this blockchain is rejected because these blockchain continue to add, and this was a wrong block. So what happens? These instructions are again added at some other level. So that is how this double spending attack can happen. And how this if the person doesn't, the person waits for all the confirmations, then he realizes that the transaction has not come through. So he will make only the transactions to one person, right? Buyer succeed in double spending by sending a confirmed transaction to seller A and rejected transaction to seller B, but receive the services. It is the mistake of seller B. Otherwise, double spending attack is not possible, right? Then there is a 51% attack when a single miner or a group of miners or the pool of miners, you call it, if they attain majority of the network's hash rate. If I can have more than half of the power, let us say 7 people have to approve. If 4 of them are from my side, right, then I have a majority. And if 3 of them are still not agreeing, if I can get other friends of mine to approve it, and it gets more yeses, then it becomes this thing, right? So the effects are it prevents transaction and blocks from being verified because you have immense power. Now you can approve what transactions you want. You can make your own transactions and you can approve those transactions and all, and they get added to the blockchain. So you can reverse transactions to allow double spending. You can prevent other miners from finding any block. You can create a denial of service attack, and then lastly, you can also fork the blockchain. It can happen when there is centralization by pools. Pools, as we discussed already, mining pools. People are coming together to become a pool, and then they acquire more than 50%, more than half of the hash power, and then it's easy to implement in altcoins because to control 51% of an altcoin network, only a small portion. Like if you are working with Dogecoin, you don't need blockchains, bitcoins, what do you say, a part to come and verify, right? So that is something which we talk. In order to control the 51% of an altcoin, so normal Bitcoin, what cost will happen and what cost or what effort has to be done for Dogecoin will be comparatively less. So, so that is something that you can do. So basically, only a small portion of the miners from large coins need to switch as a smaller coin, right? Then extremely expensive for popular blockchains like Bitcoin and Ethereum, because they are both very popular, and then a lot of smart contracts are being built, a lot of crypto codes are being built, so it becomes very difficult. So then it gets much cheaper quickly for newer blockchains, like simple blockchains like Dogecoin. Very easily you can do it, right? So maybe if you look at 1.5 million is required dollars, 1.5 million is required to execute a 51% of Ethereum Classic with a market cap of $2 billion. Right? So that is something that you can try to look at, right? Ethereum hard fork, Ethereum Classic suffered 51% attack 3 times. Attack can be identified by unusual high rate of orphaned blocks. A blockchain dash uses a secondary validation layer called chain logs. So you can do that. It prevents a block reorganization by making it expensive for the attacker. Then there is another attack called selfish mining. We talked about double spending attack. We talked about 51% attack. We are talking about the third attack called Fisher mine attack. A selfish mining attack, right? Not the Fisher mining attack, selfish mining attack. In the selfish mining attack, what happens is there is a block which is created. So block 1, block 2, block 3, and so on. Block n is created. After block 2, so many blocks are created. Block n is created. And on one side, block n plus 1 is created. And a selfish miner, what happens is he creates block n plus 1. So usually after he creates a block n plus 1, he must actually announce it to the blockchain. He must add it to the blockchain here. But what he does, he doesn't disclose. He calculates the next block n plus 2. While there are some honest miners, they mine the block n plus 1, and they have taken some time for its validation. Then it goes to the next block. That is the another this thing. So you try to add that there. So this thing is going on. But the selfish miner, what happens is he mines 3 blocks, 4 blocks at one time. And as he sees the time here, he releases these 3 blocks all at once. Here there are only 1 block or maybe 2 blocks at the most, but then now here you have all the 3 blocks are created and 3 blocks are announced at one time. That's why you see that 7, 8, 9 minutes. Usually it is a 10-minute difference that is there on the blockchain creation. But then here, when they are selfish miners like this, they will issue them blocks one after the other in no time. So what happens? The blocks are coming, and because of the blocks are coming, so suddenly this line becomes bigger, and because this line is become bigger, those blocks which are actually the honest blocks, they are nullified. So these blocks, you earn more money, and you are actually you are making via media make. So it is when the miners deliberately keep their blocks private. Upon discovery, they continue to mine their own private blocks to obtain a chain longer than the public chain, and then they release the private blocks for higher rewards. So this is a selfish mining attack. DDoS attacks can happen. You know what is a DDoS attack, and very easy to launch DDoS attacks. You can launch DDoS attack on other miners, right? So other miners are making more blocks, so you want them to be out of the network. So what you do, you launch distributed denial of service attacks on them. So they are disconnected from the blockchain network, and then they don't know what are the new blocks and how they are creating the blocks, and then they lose out on that. So the DDoS attacks. Honest miners waste time in verifying fake transactions, reducing their chance of mining the block. So sometimes there are fake transactions which are targeted, and when you work out, so you get a block, and then you analyze the block and then do all that analysis and show the results. But by that time, actually the attack has not happened. So hence you can say that this is how this thing happens, right? So the next attack is a network attack. Network attack is basically goal is to isolate a user from the real network and lead them to a fake network. This is the actual blockchain network. Here, this is where he wants to go, but he doesn't know how to go. Then you have a DNS entry which is made, and based on the DNS entry, you should be able to go. But actually, what is happening here is this cache is poisoned, and because it is poisoned, so what happens is poisoned by this thing. right? So what you do, you change the addresses. The blockchain network, it should go here and come here, but in spite of that, you are actually going to another place. So this fellow has actually created this attack this. So this user wants to actually go here, but this user is sent here. So this is how. So when a join node, when a new node joins the blockchain, it is bootstrapped to some DNS nodes to download the blockchain. So that's what actually happens, right? So fake entry point nodes return to the user. So user could be routed to some alternate network rather than current blockchain. So when a group of malicious nodes isolate its neighboring node, compromise their incoming and outgoing traffic, they change the blockchain view of the honest node, feed them fake information regarding blockchain and transactions. So here you see when honest nodes attacked by red malicious nodes. So you see that. So these are the nodes, and these are the blockchains which are there, right? So there's an eclipse attack. The malicious node then send fake transaction and blocks to these nodes. So the honest nodes are attacked by the red malicious nodes. So this is called an eclipse attack. Then most of the time we see that nobody can understand the data, but then there are some privacy attacks. So usually it is anonymous. By looking at any of these transactions, you can't know who the transaction is, but each user is identified by each address only and can generate as many addresses as required. So now you can generate alias addresses. So it's not that only one address is there or one email ID is there. You can operate multiple email IDs. So that's an example. And a blockchain is replicated at each node. An observer can use the transaction history in blockchain to find the topology of the network, patterns of the transactions, patterns of the user's transaction. These are privacy issues, right? By looking at all the transactions and the transaction history, you can actually find out how many topologies exist, this thing, and then patterns of the transactions and patterns of user items, right? User can be mapped to its geographical location using network information. So as you see, US, Australia, and other countries where a lot of Bitcoin nodes exist. So this is a kind of information which has can be taught. And the transaction can be developed to study the flow of Bitcoins in the network. So user network can be developed to study the ownership and spending patterns. So here you have the one address, and then you have these two addresses, and then you have these two more addresses. So each time these addresses are different and these addresses are same. So it is coming back to the same location. So this is what is a privacy attack. So using transaction patterns and information gathered off the network, and network means the storage data, the huge database that you can build of some 7 million blocks, all the transactions and all, right? So all these things will be there. And then using a transaction, the information gathered off the network, an adversary can attempt to de-anonymize the users. Anonymity is users are not known, but sometimes you can de-anonymize the users by mapping their Bitcoin addresses with their real world entities, making anonymous. So sometimes they are actually not fully anonymous, they are pseudo-anonymous, at least some region may be known. Sometimes payment can be made to a vendor, and the vendor gives an address, and that address is mentioned on this thing. So what you can try to do is very easily, you know that somebody has purchased this vendor's products. So that is also a privacy issue. Why you purchase, how you purchase may be a different issue, but whether he made a payment to this this particular this thing, so that's a vendor address, and if the vendor address is popular, so that is how these things can happen, right? So this is so you get this address which a user describes it on the website, and then now you show that this person so and so ID. You can try to find out, right? So payment to a vendor whose address is scrapped off the network can actually give you insight into who is buying. So you can make a list of these addresses and find out who all made transactions to these addresses, and then you can build a big list. So that's the kind of thing. And when you have 5 addresses here on the left hand side, and they are all going to one address on the right hand side, you can realize that these 5 addresses belong to the same gentleman, right? So that is something that you can look at. Transaction analysis, again, as you see, 4 Bitcoins are there. So there's a transaction 1 which is happening. It is giving 1 Bitcoin at 4 Bitcoins. 3 Bitcoins. 3 Bitcoins is basically though you have, this is an original address, this is a change address, this is a recipient address, this is where one is going, but you are sending it back to yourself, but you get a different address, right? That's called a change address. Then you give 1 Bitcoin, again recipient two's headquarters, and then that is also returned. So it is again coming back to your address. So it is coming back to the same address. So all change addresses and original addresses belong to the same. So this original address, the change address, and the circular and the other address all are shown. Now, basically, cryptocurrencies are used for illegal activities. As we know, a lot of digital these things are there, where you can use it for money laundering, you can use it for illicit activities, you can use for irreversible scam activities and all that. And there is no central agency where we can claim fraud and expect. So blockchain applications, as we look at, there are some scripts you can write on blockchain. On Ethereum, you can write scripting, smart contracts, and then you can run those codes. And then there are variety of scripts which are written in blockchain, and they can readily use it. And very simple data is stored and the program executes. But where are the applications? Applications are in supply chain management. Applications are in healthcare. All the medical records, all the doctors' reports, they are all can be stored on the blockchain and retrieved by people who have the rights only to do that, right? So that those are things. And then there are many more applications which are there. So one of the things that you can write scripting in Bitcoin Core, it's called script. In blockchain Ethereum, it's called smart contract. So code that facilitates, verifies, or enforces the negotiation or execution of a digital contract is said to be a smart contract. And smart contracts can be very easily written on Ethereum, right? So, you need to know the languages called Solidity and Viper, so that Ethereum reacts to external world when poked by transactions. So these are smart contracts. So they are two people agree on a smart contract to run on an Ethereum network. So Ethereum supplies the input price and this thing, and then on the other side, the other person receives the this thing. So that's how it is. So it's a kind of a smart contract, right? So it is written in languages called Solidity and Viper. Now, Solidity, you can go and read the documentation, and then Remix is one of the one of the editor, like where API this thing interface environment where you can go and die. So that is something. So you can use the editor called Remix. Remix has Visual Studio Code. It looks like similar to C hash and all that. You can use them. This is a sample code, a simple smart contract to mint and send coins. So a lot of activities, and then you are sending the activities. And attacks in smart contracts, the reentrancy attacks. There are some problem in this implementation of the app. So they have when they make recursive calls to call.value on the smart contract, it happens. It happened in 2016. It's called Decentralized Autonomous Organization, which was created in 2016, and then it was supposed to act as an internet academy. Less than 3 months, the distributed arrangement, distributed autonomous organization was hacked, and 60 million was stolen. So these are what is called DAO vulnerabilities, where withdraw balance calls itself again and again. So these are some things. The withdraw balance function can be called many times. So this can also result in loss using smart contracts. If the code written in smart contract is not secure, it may lead to some attacks called overflow attack, forced balance transfer attack, and then DOS attack. So this is something that you can tend to understand. Now, let me introduce you, because I have less time. So before we take up questions, let me quickly introduce a privacy preserving blockchain. It is by inbuilt. It has this mechanism of doing that. So it uses what is called a stealth single use addresses or ring addresses, also called confidential transactions. We'll see what it is. So monolithic is where two people are making two transactions, and finally charge is listening to the transaction, right? So the whole world, when it looks at the transactions, Charlie, it sees Alice and Bob are making transactions. So they know, the whole world knows that these two people are making a joint transaction to Charlie, or somewhere these transactions are coming together and A and B are giving money to C. So, but otherwise, we try to create an unlinkable transactions, right? The unlinkable addresses will mean ours is Alice is sending, making a transaction one, the address is not mentioned. Bob is sending a transaction, but it is also not mentioned. Charlie knows that both the addresses belong to me, but an outside world thinks no idea where the transactions are going. This is called the unlinkability. The different destination addresses for each output is derived from one Monero address. Only the owner of the Monero address knows that output is for him. Nobody can tell these inputs. Second one is untraceability, where there are three transactions which are coming and they are doing transaction one. And the transaction one is basically made on these some addresses. So you have transaction A, which is pointing to some addresses, and then you are trying to look at transaction one is spending funds received in transactions A, B, and C. Transaction one is spending once in spending the received in transactions A, B, and C. But otherwise, if these three transactions A, B, and C don't point to these some addresses, but they become three different addresses, and they are pointing to some addresses, and finally you have the transaction made to the Charlie's address. So everybody is able to see transaction one is based on the funds received from A, B, and C. And in case of this thing, so the world says no idea where the funds are spent in the transaction. The second one is called a Monero ring signature. So Monero ring signature, at least one real participants and others are called mix-ins. Mix-ins are outputs from some previous transactions. They're already been used, so they are mix-ins. So they form a real signature created to sign the transaction. So what in this case happens? So for some outputs in the blockchain with the same amount X, so you may have to make some 10 transactions, in that 5 transactions are the same amount. So what you do is you add more mix-ins and send them across, right? You can use 4 to 25 mix-ins in a transactions, right? So you can use this mix-in technology to be 5 this thing, and then 4 to 25 mix-ins can be added. So this is how it happens. So you have 3 Alice, Bob, and Carol here trying to access. So it's easy to verify that at least one user from the inputs have signed this ring transaction, but we don't know who has signed it because nothing is mentioned in the blog. So mix in one, output A, X Bitcoins has to be transferred. Real B, X Bitcoins has to be transferred. All these things are same. So only that the dark shaded portion is said to be the real input. The other 3 blue ranged boxes are said to be what do you say, mix-ins or transactions which are not important. So what will be the new transaction? You have a reference of output A or output O or output B or output C. Output is Bob's address. So that is something that you can look at. So the output of the mix-in. So only one value goes in. So Bob's address is the output. So you get that this is how ring signature is used. Lastly, we have this confidentiality where we don't want even this money to be displayed, right? So we use what are called, we try to hide the transaction amounts to provide financial privacy. So Monero is one of these. It's called non-interactive zero knowledge proofs, NIZK proofs, non-interactive zero knowledge proofs, right? So they create confidential transactions. They prove that their encrypted input and output of a transaction are in the given range, and without revealing any other information, it goes on. So they use this concept called Peterson's commitment, which is G power H3 and HR1. So Peterson commitment is mentioned. X of R is G of X into H of R. So this is something, and then G10. So G10 H3 HR3. So you can try to look at that and calculate it the next value, right? So this is what is called Peterson. So using Peterson commitments, all transaction amounts are hidden. Transaction graph is still public and allows public variability of transactions as well. So this is what it means. So the transaction components, so sum of inputs is greater than or equal to sum of outputs. Some of outputs are positive, right? So this is a little bit background of cryptography behind the Peterson commitment. If you're interested, you can go through this, right? So this is how it is, and then there are a variety of proofs. So one proof is no idea what X is positive, but it's positive, and Peggy must know it. So that's how they try to do that the wrong way. So I will stop here, and if there are any questions, we can take it now. I will be shortly sharing the slides, so you can take it forward. Any questions, I will be very happy to answer. Of course, I will tell you in the beginning, this is the first time some of you may be listening to blockchain, and also security issues in blockchain is a very important challenge, and it will take time to digest. But then there are important aspects like what you call this thing, which is uh, it is said to be there is a important paper on attack surfaces on blockchain, so you can read that. I will share that with you. Then I will also want to share two strategy papers that are there on blockchain, so you can look at those strategy papers also by Government of India, right? You can look at those strategy papers, one by Niti Aayog and one by Ministry of Electronics and Information Technology. You can look at those papers as well, right? If you have any questions, meanwhile, I will try to open those papers where you can view later. If you have any questions, you can use the chat to drop in the questions. It takes time. Go through my slides again and slowly go through the Andersworth Brown this demo also. Slowly you will understand, and then you can start thinking. And then maybe if you have any questions at that time also, then we can, right? So that's something that we can. Yeah, meanwhile, you can try to look at any questions if you have. I'm just trying to identify this thing.
Participants,
Any questions? Please?
Any questions, please? You may unmute. Pramod sir, do you want to ask something? One query from Pramod Pal sir, I can see in the chat box.
Yeah.
How can blockchain security breaks?
How can blockchain? Yeah, as of now, blockchain is very secure. You cannot break blockchain security. But then, yes, there are privacy issues. You can try to get some information and all. The biggest threat is when there is the 51% effect in the picture, where you are able to get the control of the mining process. Because I talked about confirmations, but I did not show that actually. So you need to receive at least 7 confirmations from miners. Once a miner adds it, the 7 other miners must confirm. So once the confirmation done, then only the block can be added, right? So because you are also calculating the nonce value, I'm also calculating the nonce value. I will take the same transactions, you will take the same transactions, and we'll calculate. We get the nonce value, and then we add the next block. So immediately others will also get the same result, but they may have got it little late. So what they say, anyway, we got the result. Okay, his result is correct. His result is correct. Like that, 7 people should say. If you have such 7 people in the whole world who compete at your level, calculate that value, and when they know that it is your value, they will immediately say yes, 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 yes. So if you can create such an environment, right, then you can take over the blockchain. That's where the blockchain security will break. Otherwise, it's not possible. The other thing is, if you have a very powerful resource, then only you can take over this attack. And for that, you need what is called this 50% of these things that are there. So that attack you can try to get it, right? So that 50% of the resources, maybe if a quantum computer comes up today, GPUs, clusters, all are not able to really take over the 51% attack. Maybe if a powerful computer comes in, which will work faster. But then I'm sure, like how the ASIC resistant mining algorithms have come, the quantum resistant algorithms may also come for mining, right, at that time. So that change will still be there. So that is the point.
More questions, please.
Yeah, for digital signature, what are the digital signature? I don't think there's any digital signature which is used in the blockchain. But yes, for the encryption and all, if you are thinking on that lines, it is elliptic cryptography, ECC that you have. So that's what it is used for that, right? But otherwise, the hashing algorithm that is used is SHA, secure hashing algorithm 256 is used. So these are the things that are used. So the remaining algorithms are mining algorithms. They're called consensus algorithms. So proof of stake and proof of work. Proof of work was earlier. Now it is proof of stake.
Any other questions, please? One more query. Is ECC is having a wide scope in blockchain? So I could see in the chat box.
Is ECC having a wide scope? Actually, the underlying construction is basically built on ECC, right? So if you want to go back and understand the actual construction and how things are being verified, that's where ECC will come into the picture. There is a book, maybe if you can want to read that. I don't know whether it is available on the public access, but you have Arvind Narayanan, Bitcoin and cryptocurrency technologies. That's a book, right? So you can try to look at that, and then you can try to look at those Bitcoin and cryptocurrency technologies, a comprehensive this thing, right? So that is available by Arvind Narayanan, right? So in that book you can try to look at the what is the scope of ECC, right? Any application of blockchain in bioinformatics? Yeah, see, blockchain can be used in cases where the applications will need a value should not change, immutability, right? Blockchain is immutable. Any transactions, any values that are stored on the blockchain cannot be changed. So those values are called immutable. So any property like that you need, then you should go to blockchain. Otherwise, there is no need, right? Like a DigiLocker kind of an application, a land records kind of an application, your medical records which should not be changed and which should not be transferred. Land records should not be changed and tampered with, right? All these can be put on blockchain, right? So bioinformatics. Specifically, I'm not sure, but any health related issues, if you want to store the data which should not be changed, so that's where blockchain will be used. And of course, now blockchain can be used to run a lot of these contracts, smart contracts agreements. So you can code and you can put it. If you want to store data, also you can store in form of transactions. Instead of making the transaction, you can store the data also. For storing data also, you will obviously need to pay a transaction fee. That's the only issue. So that is something that you can try to look at.
Any other queries? Any application in deep or machine learning, it is there in the chat box, sir.
As of now, if you would like to look at machine learning, you can take the data that is available in a blockchain, public blockchains, especially like Ethereum and Bitcoin blockchain. You can download this entire data set, and then you can try to build build relationship between addresses. You can take one address and you can find out who all made the transactions with these addresses in all those 7 log blocks. So about 800 GB of data will be there, and you can download that 800 GB of data, and then you can do a lot of machine learning, and you can build a lot of privacy preserving algorithms. You can build on that. So you can calculate a lot of algorithms which you can pick up from there, and then you can easily do that. So that's one thing. As a data mining kind of thing, you can do that. Right? So that's something. I don't think you will have anything to do with deep learning on blockchain because the data is not that big. But of course, machine learning you can do on 800 GB of data. You can do a lot of machine learning. You can do a lot of privacy preserving techniques you can build. Privacy enhancing technology symposium has a lot of algorithms which run on blockchain, right? PETS. It's a very good conference. Call for papers is there every quarter. A conference is held only once a year, but you can submit in 4 quarters. And 2 quarters get published in 1 year, and the next 2 quarters go into the next year's publication. It's a very good conference. Privacy Enhancing Technology Symposium, PETS, right? So you can look at different machine learning algorithms. In supply chain management, yes, all entries that are going, supply chain management, you have a lot of these things which are going out, maybe as we call them containers, right? Each container will have this thing, and that container can be stored on the blockchain. So medical records are stored on the blockchain. Similarly, the container's data is stored on the blockchain, and it cannot be changed because it is already logged there, right? And anybody can verify the details and then hand over it to the vendor that who is looking for. So that's kind of thing that can happen. So that is. Yeah, there are no questions. So over to Dr. Latika or Dr. Dolly.
Okay, if there is no query, then we can wind the session here. Thank you, sir. Thank you for giving a brief description about the Bitcoin and this blockchain management system, security systems. Thank you, sir. Thank you very much.
Okay.
All the participants are requested to fill the attendance. Attendance link has already shared in the chat box.